Okay, so today is lecture 2 for our course in waves and optics. So I'm going to start the screen show here. And I just want you to recall from the last class that we derived a wave equation that will allow us to, that represents a solution for the waves that we had derived. And waves, we saw that all general waves that retain their pulse shape or form as they propagate are of the form psi equal to f of x prime, or x prime can be either x plus or minus vt. And we also saw a specific case, which is called a harmonic wave, that I'll talk about next. So what we're going to do in today's lecture then, continuing on from the last one, is we're going to finish up the discussion of harmonic waves. We're going to introduce a superposition principle for waves, and then we'll move into 2D and 3D waves, where we'll discuss different types of wavefronts, plane waves, spherical waves, and cylindrical waves. And finally, I'll talk about rays. All right, so in the last class, we talked about harmonic waves, and we saw that function of the form sine kx at time t equal to 0 represents this harmonic wave, and it has a period of lambda, which is the number of length units per the wave, which is the spatial period. A is the amplitude, and then we also reserve the word, the symbol phi for the phase, which is 2 pi over lambda times x in this particular case. The reciprocal of lambda is called the spatial frequency. We also showed that because of the fact that this must satisfy the wave equation, that k should be related to lambda as 2 pi over lambda. And since lambda has units of length, the units of kx will then be radians or phase, as we already discussed. We can also use other types of profile elements. So for example, this shows that instead of taking a sine wave, we could have taken some other shape, different shapes that are shown in part B of this figure to form a wave that's shown in part A. As long as you tile it or repeat it at a wavelength lambda, that will form another wave with a wavelength lambda. We can also see that the spatial frequency can be used in 2 dimensions. This is just a quick example that if I took that same sinusoidal waveform and now represented it by these bright regions wherever the wave was a maximum and a dark region wherever the wave is a minimum, then the spatial wavelength, if it's long, gives me the pattern which is on the top. And then if the pattern on the bottom is representing one where the wavelength is much shorter. And this represents, since the spatial frequency is the inverse of the wavelength, the top one will represent a brightness profile with a low spatial frequency. The bottom represents a brightness profile with high spatial frequency. And in fact, we can show later on in the class, we'll see that almost all images, or most smooth images, etc., can be represented as combinations of various brightness profiles with different spatial frequencies. Now, that is just about the waves in the spatial dimension. Now we're going to introduce the time dimension. And in the time dimension, the way to look at it is here on the topmost graph, I plotted a wave with a wavelength of over one wavelength period, lambda. And the maximum point of this wave is this point over here, which represents a phase of pi over 2, right? And then as time goes on, we see that the wave propagates to the right. And after a time, for example, tau over 8, it'll propagate by a little bit to the right-hand side. After tau over 4, you see it is propagated by a phase of pi over 2 over here, right? It's the point of constant phase has shifted by a distance lambda over 4, as you can see here. And then similarly, as we keep going, eventually at a point t equal to tau, that is after a period tau, the wave has shifted by an entire wavelength. And as you can see, the rest of the wave that was lying to the negative x-axis is now visible going in this grayed out region. And the dark region represents the original wave that we had started with. And so after time period tau, the wave travels by a distance lambda. And I should also mention that it is this point of constant phase that's traveling, or the point that represents the phase of pi over 2 that's traveling, because the point where originally the wave was at this maximum, the point of the medium, let's say if it is a string, or if it is an electromagnetic field, the magnitude of the electromagnetic field there, etc. None of those is actually moving from left to right. So you can see that at the point lambda over 4, which is represented by this little dot on the wave, that point just travels up and down vertically along the wave function axis. In this case, the wave function could, of course, represent just the amplitude of a magnetic field or electric field. And this value here moves up and down harmonically, right? Over this whole time period, tau, it goes all the way from the point over here, goes down at a point t equals tau over 4, it has reached this 0, and then it goes and reaches the point t negative maximum at t equal to tau over 2, and then finally when it comes back to t equal to tau, this point has returned back to its maximum value. And so this represents in fact a harmonic motion. It's an oscillatory motion in the vertical direction. We also in this graph have shown or in this figure we show a second sort of clock or an arrow that represents a clock that you can think about. This projection of this arrow along the vertical is the displacement of the wave at the point x equal to 0. If that's a little confusing, don't worry too much about it. We'll come back to this when we discuss phasors. But it represents another way of thinking about the wave, which is its projection of this arrow along the vertical will be that displacement at that point x equal to 0. So since the wave must repeat after a time tau, as we've just seen, so in a time going from t to t plus tau or t minus tau, the wave function must remain the same. So we can immediately carry out our usual analysis where we take x, we displace it by vt, because we know that sine kx and sine k times x minus vt must be the same. And that must be the same as this function on the right-hand side, which is x t plus or minus tau. So by equating the leftmost to the rightmost, and since the only way for the sine function to repeat is if this extra factor here must be equal to a multiple of 2 pi. So if you set it equal to 2 pi, then we get v times tau equals lambda. And this is a very important relationship. As we just saw from this right-hand figure, after a time period tau, the wave has traveled by a distance lambda, which means we can define a velocity for this wave, right? And this velocity is in fact this lambda divided by tau. So you can say that tau represents the number of units of time per the wave. So 1 over tau is the number of waves per unit time. And this waves per unit time is called the temporal frequency nu, or simply sometimes f. And as I just showed you, v must be equal to lambda times nu or lambda times f. So at any given point, if I sit at any one point, let's say the point denoted by this little dot over here, the number of waves that sweep by that in a unit time is f, right? And therefore the interval between waves is tau, as we've just seen. The length of the waves is lambda. Therefore, in a unit time, the length of waves that sweep by you is again lambda over lambda times f. And therefore, again, we have rederived in this way that the velocity of the wave must be lambda times f. You can also define the angular frequency, just like k was the angular propagation number or angular wave number. We can define the angular frequency as 2 pi times this regular frequency f or nu. Okay, so 2 pi nu or 2 pi f is the angular frequency of the wave. So monochromatics harmonic waves, which means that they have a single frequency, can be represented by many different forms, which are shown here. So psi can be, as we've already derived, a times sine k times x minus plus vt, or it can be represented as a sine times kx, sine of kx minus plus omega t. The minus sign representing wave traveling to the right, and plus sign representing wave traveling to the left or negative direction. We can also rewrite that same formulas in these 3 other different ways, which are shown over here. But the most commonly used forms are these top 2 forms over here, which are in the green box. So now I want you to answer this question, which is that if you are sitting in a boat watching an endless set of crests cross by, and the time between the crests is 0.5 seconds. The disturbance seems to take 1.5 seconds to sweep along the length of the boat, though the length of your boat is 4.5 meters. And the question is, what is the wavelength of the wave? Continuing on with the history of the field of optics, in the 20th century and the 21st, coming in through the 21st, there have been many Nobel Prizes that have been awarded to the field of optics, which includes both, I guess, visible optics, but also includes things like X-ray optics, starting with the discovery of Roentgen in 1901 of X-rays, and proceeding systematically. You can see all these different Nobel Prizes up to the inventions of the laser and laser cooling, which is used to, like nowadays, create Bose-Einstein condensates, and moving on up through, that was in 1997 was the invention of laser cooling, and then a few short years later, 2001 was when the first Bose-Einstein condensate was found. And I should also mention Zernike in 1953, who discovered electron microscopy, and moving up through to the most recent Nobel Prizes, which include some in chemistry and medicine as well. But in chemistry, Bedzig, Morner, and Hell invented a new type of microscopy for sub-diffraction limited microscopy, which has been highly useful in the fields of biological physics and medicine and so on. So as I just mentioned, that was about the field of all the different discoveries in the field of optics in the last 120 years or so. So one of the things that I mentioned already is that the dual particle wave nature of light can be pretty confusing. And it in fact confused some very brilliant and famous scientists such as Newton and Huygens, who were feuding about this back in the 17th century. Nowadays, we take on a modern view of this, which is that a beam of light, where we are thinking of the beam of light as delivering energy from one side to another, this beam of light can be thought of either as a flux of particles. These particles are in fact massless, as we know, which are called photons. And that is actually very similar to what Newton had envisioned back then, although he had some different properties for these photons that we now know are not right. But at least he was on a similar track as what we think are the particles of light now, which are called photons. And they are these zero mass particles that can travel at the speed of light, whose energy in each case is carried by E equals h nu. Nu is the frequency of the associated electromagnetic wave. So that's what makes the connection between the electromagnetic wave and the energy of the particle through the Planck's constant h, which is defined here, which I'm sure you've all heard about or seen before. And you can see in this picture what electromagnetic wave. This is a 1D representation of an electromagnetic wave, and I'll come back to this in a little while. But this shows that the wave moves at this velocity c, which is the number of waves that, or the length of the waves that are crossing a certain point in a unit time, right? So it's lambda is the distance between the waves, that is one wave, and the next has a distance of lambda, and that crosses the point where you're sitting, let's say, every 1 over the frequency or the time, which is equal to the time period. I'll come back to these definitions, but the time period essentially represents the time between these waves crossing. And from that, you can easily derive this relation C equals nu lambda, which is so-called dispersion relation in free space, and that connects many of the properties of waves and the speed of light, as well as the energy, as you can see, of each particle is connected through the Planck's constant and the frequency nu. So that is the sort of the dual particle wave nature of light. And we know now that every as I just said, every electromagnetic wave which is characterized by some frequency or the inverse, which is related inversely to it, which is the wavelength, these form a spectrum. So these electromagnetic waves form a spectrum all the way from gamma rays, which are extremely short wavelengths, below tens of nanometer. Those are typically emitted by in nuclear reactions. And then as we proceed increase in wavelength or decrease in the frequency, we start to get to the regimes that we are more familiar with as electromagnetic waves, such as X-rays, ultraviolet rays, which are emissions, say, from the sun and in other processes, chemical processes, and then moving on down into what we think of as the visible spectrum, the light wavelengths that we normally think about when we are thinking about light. And that ranges from blue through red, wavelength, very small wavelength region of 488 to about, or 400 to about 700 nanometers. It's also represented in microns as 0.4 microns to 0.7 microns. And here in this, I'm showing also the different wavelength regions, or the wavelengths that that are typical characteristic wavelengths that we think about, like blue, which is a laser that's available quite easily in the blue wavelength region, 488 nanometers, with a frequency, as you can see, of 6 times 10 to the 14 hertz. So typically the frequencies of electromagnetic waves are in the terahertz, hundreds of terahertz, as we call them, terahertz being 10 to the 12 hertz regime. And then as we keep increasing the wavelength, we get into the infrared regime of a micron to about 10 microns. And then beyond that, we reach what are called the microwave region of the electromagnetic spectrum. And then even longer wavelengths are the radio frequency waves of the electromagnetic spectrum. So that this is another picture. This was taken from your textbook. So you can go back and look at these same wavelength regions. You can see, in addition to the wavelength in energy, in wavelength and frequency that I was just showing you, he also shows the energy, photon energy. And so you can kind of roughly see 1 electron volt is roughly the energy region that we normally are sensitive to with our eye. And that is the region of visible light, which is this gray band over here. And then all the other energy regions. So 1 electron volt is, like, I think, a nice way to remember it. It's just the approximate wavelength energies of visible light. And then all these other spectrum are either orders of magnitude above or below that, as you can see. And on the right-hand side, you can see all the different sources that we normally have and the different detectors that we have for these different kinds of radiation. Another question we can ask is, what separates the behavior, or how do we distinguish between these particle and wave? And as I told you at the beginning, we also have the geometrical or ray optics picture of this of light, and the relationship, it turns out, is governed by this interplay between wavelength and the dimensions of the equipment that we use to study the light processes. So the way in which the light propagates and the way in which it interacts is also just as important. The way it interacts with the equipment that you're using to study it also makes a big difference to the pictures that you're going to see or the kinds of behavior that you're going to see. And that is summarized here. When the wavelength is far lesser than the dimensions, or the photon energy is far lesser than the energy sensitivity of the equipment, you're going to see a geometrical or ray optics picture. And then when the wavelength becomes comparable to the dimensions, but the photon energy is still much, much lesser than the energy sensitivity of the equipment, you see the wave optics picture. And when the wavelength is far lesser than the dimensions, but the photon energy is greater than or comparable to the energy sensitivity of the equipment, you reach the photon picture or the quantum optics, quantum electrodynamics type of pictures that, that we study. And if you really want to understand this full theory of how to unify all these different behaviors and all these pictures, you have to study quantum electrodynamics. So don't stop, don't pass go straight to grad school, okay? All right. So that's how I like to think about or distinguish and sort of, in my mind, use this to sort of think about what descriptions are most likely to be appropriate for different regimes or different interactions. And you can already see that the way in which a field, a quantum electrodynamics field interacts with your observer or the equipment is going to govern a lot of this ideas or these pictures that we are going to use to study them. But I can tell you right away that for about 90% of what we do in the lab, the geometrical optics picture is going to be good enough because the wavelength of visible light, as we just saw, is less than a micron, right? It's about 0.4 to 0.7 microns. So unless your the dimensions of your slit or the photon energies or the energy sensitivity of your equipment is approaching, say, an electron volt or something like that, it's only then that you're going to start behaving with some, something akin to photon or quantum optics that you're going to have to worry about it. So that is, so the geometrical optics pretty much will be working for most things, but we can indeed see the wave optics picture, as you know, in the lab through like various experiments that we're going to do in this course. And then we can also see some of the photon or quantum optics behavior. We just have to sometimes increase the energy of the photons or just decrease the dimensions of the equipment. Okay. So let me now talk a little bit about the wave propagation, and from that I'll quickly move to, because I think it's good to start with this wave picture, and then we'll quickly specialize into the ray picture because that's where a lot of the initial experiments that you're going to do in the lab are also going to be carried out. But I think it's good to have a basics of wave propagation in mind when we do these ray optics. So what is a wave? A wave, as I define it, is just a self-sustaining disturbance that conveys energy from one point in space to another, sometimes accompanied by motion of the material in the medium. So here's a medium, in this case, is just a slinky, right? You all played with slinkies, I'm sure. And if I push on the slinky in the same direction as the length in which as the direction in which the slinky is wound, then you see these little disturbances that are propagating in the slinky, and which is governed by these increasing density or increasing compressions of the slinky in different regions, and then expansion of the slinky in different regions. And so, as you can see, that disturbance, which is that little pulse of propagation along the length of the slinky, goes from left to right, and such a wave would be called a longitudinal wave because you can see the displacement of the slinky is in the same direction as the propagation. We can also displace the slinky transverse to the length of the slinky, and as you can see, in that case, a pulse with a certain height, in this case a displacement in the vertical direction, will propagate from left to right unchanged. And another example of this is, for example, if you take a string which is tied to, one end of it is tied to a wall or some hook on the wall, and then you shake the end of your rope, the string, then you're going to see a wave that's propagating from left to right. This displacement of the shape, the pulse shape, is going to propagate from left to right. So since the disturbance is moving, it must be a function of both time and position. So we can immediately write down that the disturbance psi of x comma t is some function of x and t, where f we typically hope will be a smooth differentiable function for most physical situations, right? So f of x comma t is a smooth differentiable function. So if I have the shape of the wave at time t equal to 0, psi of x comma 0 must be f of x comma 0. And so let me just see if I can get a little little arrow here to show you. I'm not sure you're able to see my arrow, but so well, I'll just keep going. So the wave at t equal to 0 has a certain shape, which is denoted by this little shape on the y-axis. That is the shape of the pulse shape of the wave. And in the frame S, which is a frame that's at rest in the laboratory, the wave is propagating, in this case, from left to right at some speed v. Okay. So to understand what the behavior of this function of this wave must be like, what we can say is that at time t equal to 0, this psi of x comma 0 is some f of x being a smooth differentiable function. And if I now translate myself into a frame that's moving with velocity v, which is this frame s prime, well, the shape of the wave must remain the same because the wave itself was moving with the velocity v. So therefore, if I move into a frame that's moving also with velocity v, then the shape of the wave must remain unchanged. And that is this middle graph that you see here, which is psi equals f of x prime. And of course, the relationship between x and x prime is pretty easy to see. It is that the coordinate x prime plus the position of the origin at any time t, which is given by vt. So the total coordinate x must be equal to x prime plus vt. Therefore, x prime must be equal to x minus vt. And therefore, psi, which is equal to f of x prime, must now therefore be equal to f of x minus vt. So that gives us immediately that any wave that must propagate unchanged in shape as a function of position and time must have this form f of x minus vt. So we can choose any smooth shape and replace x by x minus vt, and we'll get the same shape traveling to the right at a speed v. So as you can see here, if I take any shape, any smooth, nice shape like f of x equals this function 3 divided by 10x squared plus 1, you can see that I plot on the left-hand side the function at time t equal to 0. And then to find the function at any later time in this wave, I just replace x by x minus vt, as you can see on the right-hand side. And in this case, the v was just a velocity of 1 meter per second. So you can see at time t equal to 0, the pulse is centered at t equal to 0. And then at x equal to 0, at t equal to 0, it's centered at x equal to 0. And then at t equal to 1, it moves by 1 meter. And so now it's centered at x equal to 1. At 2 equal to 2, it's going to be centered at x equal to 2, and so on and so forth. Okay. So I now have a question for you that you will answer in the quiz. What happens if I replace x minus vt with x plus vt? And so give your answer in the quiz with an explanation. I'll just give you a minute or so to proceed to answer that in the quiz, and then you can write your explanation out as well. I'll give you a minute or so. Let's derive now the wave equation, which we can derive now from the knowledge of this expression. And for a wave shape, which is which is psi is equal to f of x minus vt, from this we can actually derive this wave equation, which is shown here, which is dou squared psi by dou x squared equals 1 over v squared dou squared psi over dou t squared. So to do that, I will stop. I'll have to share my screen on my iPad, and I hope I'll be able to do this. Okay, very good. So to derive this expression, let's see if this works. Very good. All right. So the expression that we just derived was that psi of x comma t must be equal to f of x minus vt. So, well, it could be plus or minus. So I'll call that x prime, which is equal to x plus or minus vt. Okay. And so now what I want to do is I want to, so this is equal to f of x prime, which is given by this new coordinates. And so now I have to calculate dou squared psi over dou y squared. So to do that, I'll first calculate dou squared dou psi over dou x, which is simply dou f divided by dou x prime times dou x prime divided by dou x. So that is using the chain rule of differentiation, partial differentiation. And so now I need to know what is dou x prime over dou x, which, as you can see from this expression, is simply 1. Okay. And also I can write down now dou x prime over dou t, which is, as you can see from this expression, is just plus or minus v. Okay. All right. So that allows us to now right away calculate dou squared psi over dou x squared. And that is going to be about by the chain rule of differentiation, we now have to calculate dou by dou x of dou psi over dou x, which is equal to dou over dou x prime times dou psi over dou x times dou x prime divided by dou x. And okay, so from this we obtain that again dou x prime over dou x was simply 1, and the other condition, which is that it is dou over dou x prime of dou psi over dou x, but dou psi over dou x was already shown to be dou f over dou x prime. Sorry, I forgot to write that over here, which is dou f. Dou psi over dou x is dou f over dou x prime. So I replace over here, and we immediately see that this is dou squared f divided by dou x prime squared. Okay. So similarly, you can show that dou psi over dou t will be plus or minus v times dou f over dou x prime. And if I take one more derivative, dou squared psi over dou t squared will be v squared. The plus or minus will go away because plus v times plus v is v squared, and minus v times minus v is also v squared. And we get again dou squared f over dou x prime squared on the right hand side. And so right away we get the identity then, or the equation rather, sorry, which is that dou squared psi over dou x squared is equal to 1 over v squared dou squared psi over dou t squared. And so this equation, which is the 1D wave equation, which of course we derived from this general formula for the so I'm going to stop the share here and go back to our slides. So let me just go back there. So this wave equation that I just derived for you is in fact generally true for all waves. We started with the solution and derived it, but there's other ways to derive it, which is more a mechanistic approach, for example, for a wave on a string or so on. But this approach, I think, is a little easier to follow because we start with a solution that we have seen is a very general form for any self-sustaining disturbance. And from that, we have derived the wave equation. Okay, so let me move on now to the next part, which is after we have derived the wave equation, we can also now specialize to a certain type of wave that is very, very useful and very general, or is very, it shows up in lots of different situations, which are called harmonic waves. So in a harmonic wave, the function f of x that we are going to select is a sinusoidal function. And why are sinusoidal functions so important? Well, it turns out, as we'll see later on, or maybe you've already learned a little bit in math, is that Fourier analysis or Fourier series can be used to represent any arbitrary shape as long as it's smooth and differentiable and satisfies certain mathematical conditions, can be represented as a sum of sine waves and cosine waves. So by studying the behavior of harmonic waves, we will be able to study in general the behavior of all kinds of waves quite easily. So let's now look at a harmonic wave. And in this harmonic wave, as you can see, psi of x0, remember we specialize to the situation where, say, time t equal to 0, and immediately we get psi of x comma 0 is now a sinusoid that I've defined. This sinusoid is just a times sine of kx, okay? And the quantity kx is given a special name. In this case, the quantity inside the sine, inside the brackets, that is the argument of the sine function, is called the phase phi. And a, which is the multiplier sitting outside the sine, is called the amplitude of the sine wave. And you can immediately see what this function looks like as a function of x. If I in this graph here, you can see that at x equal to, say, lambda over 4, the phase defined by this k times x, k is now given by 2 pi over lambda. And this k times x will now have the value pi over 2, and the sine function will have a maximum. Of course, I didn't say this, but when x equal to 0, sine kx is going to be 0. So at x equal to 0, the wave will have a displacement of 0. At lambda over 4, it'll have a displacement of maximum, which is plus a. And then at lambda over 2, this phase will become pi, and the sine function has a 0. So that again comes back to 0. And then when we come back again all the way to a phase of 2 pi, where we know at 2 pi, the sine function is going to repeat. And so we see that, and it repeats in the same direction, so to speak. Like I'm now talking about sort of the displacement, going from negative to positive as we pass through the 0, and or as we pass through 0 amplitude or displacement. And we see that at x equal to lambda, that's exactly when the phase becomes 2 pi, which will have the same displacement, which is psi equal to 0 at x equal to lambda. And we can continue on in this way and get the full harmonic sine wave function that you all know. The wavelength lambda that we just defined here is the number of length units per wave, right? Every unit of lambda, the wave repeats one full oscillation, starting from 0, going up to +1, and then going back down to minus a, sorry, not +1, but plus a, and then going back all the way down to minus a, and then coming back up again to 0, which is what I meant by saying it comes back to its value after crossing through the negative and the positive axis. Then we get a one length unit, which is lambda per wave of this oscillation, and that is a spatial period. So lambda is the number of length units per wave, or the spatial period. And then the reciprocal of that, which is given a special name kappa, is 1 over lambda, is the number of waves per unit length. And that is given a name, spatial frequency, or the wave number. So we can immediately derive this relationship between the x and the time and the wave in this manner. So psi of x comma t, we know, must have the form sine kx minus vt, right? Because we know that any wave, any function of x, if I just replace the x by vt, or the coordinates inside by vt, we will get back the sine wave. So if I follow this chain of argument, at the same time, we know that by displacing it by lambda, we must also get the same wave back. And so we immediately get this condition, sine kx minus vt plus or minus 2 pi, from which we get the condition that k is equal to 2 pi over lambda. Or k lambda must therefore be equal to 2 pi to achieve the same coordinate point in psi. K is now given the name angular spatial frequency. That's because it gives you a cycle of 2 pi, and that is also called the propagation number or the angular wave number, and that is this K. So lambda, as we just showed, has units of length, which is typically nanometers, let's say, or microns. 1 micron equals 10 to the minus 6 meters, and 1 nanometer has 10 to the minus 9 meters. And therefore, we expect that these are the typical units of, say, visible light that we are going to have. And you can see that these are extremely small dimensions. That's why it's very hard sometimes to tell the wave nature of visible light, as I mentioned. So one obvious question then is, what are the units of kx? So I will let you answer that. I'll take a minute or so and let you answer that question in the quiz. Okay, so I'm sure most of you got the answer. Which is that the dimensions of kx are radians, which is dimensionless. So let me, I think at this point, I want to conclude today's lecture by just summarizing all the things that we have discussed. So the most probably, hopefully, thing that you have taken away is that waves and optical phenomena are omnipresent in our life, and they're diverse and interesting with a long and rich history. Light exhibits a dual wave and particle nature, which is understood as now different aspects of the same underlying quantum electrodynamics theory, that light behaves as a wave or particle or a ray depending on the wavelength, the dimensions, and the energy sensitivity of the measuring equipment. And we introduced wave propagation in space and the wave equation. We also defined harmonic waves, wavelength, angular wave number, and phase. And in the next class, we will proceed to consider propagation in time.